Intersection of a cone and a plane is called conic section. And depending upon the inclination of this plane, we obtain different shapes of the conic section. Let us suppose the angle between the axis of the cone and the plane is theta, and the semi-vertical angle of the cone is alpha. In this case, if theta lies between alpha and pi by 2, the shape obtained is ellipse. If theta is equals to alpha, the shape obtained is parabola, and if theta lies between 0 and alpha, shape is hyperbola. But we have one more definition of the conic section. Suppose we have this fixed line and this fixed point. Now if we want to take a point P in such a way that a ratio of its distances from this fixed point and this fixed line is constant, then locus of this point P is also conic section, where this point is called focus and this fixed line is called directrix. Okay. Today we will discuss that where does this definition comes from. I mean, in this definition there is no cone involved, but even then the shape obtained is conic section. So why this is happening? Okay, suppose we have this cone, this is the axis of the cone, and this green plane is intersecting the cone, and here the shape obtained is conic section. Okay, I have represented this green plane using 3 parallel green lines. Okay, I think there is no issue in it. Okay, now construct a sphere, draw the largest sphere which touches this cone and this plane. Now you can imagine that when this sphere is touching the cone, the contact is a circle, right? Try to imagine that you have kept a ball in the cone of ice cream, right? In ice cream cone, if you keep ball, then it will touch the cone in a circular path, right? Now draw a white plane. Suppose the point of contact of the plane and the sphere is T. Now draw a white plane which is passing through that circle on which this sphere is touching the cone. Okay, great. Now you can see that that is green plane and this white plane are intersecting on a line, and here is this line. Take any point P on this conic section and drop a perpendicular on this white plane. Say the foot of perpendicular is M. Now from M, draw a perpendicular on this line and the foot of perpendicular is D. Okay. Now join P with the vertex of this cone. Now suppose the semi-vertical angle of the cone is alpha, so you will get that angle PAO is also alpha. Why? Because if we have two lines parallel and a transverse is drawn between them, then angle over here, suppose this is A, this is P and this is M, then these angles which are shown on the screen, these are called alternate angles and these are equal to each other, right? And that's why angle MPN is also equals to alpha, right? Okay, this is the first equation we obtain. Also, since PT and PN, now you can imagine that that PA is lying on the lateral surface of cone, and that's why definitely it is passing through this white circle, and since the sphere is just touching the cone, that's why this pn or pa is also just touching the sphere, and hence pn is the tangent. And we know that two tangents on the same sphere have the same length, so pt is equals to pn. Here we have the second equation. Now angle between the plane and the axis of cone is beta. Now here we will apply another property. Suppose we have two lines and angle between them is beta, and if we take another pair of and lines in this pair are parallel to the previous one, then in this case also the angle between these lines is beta. Okay, so here we get that angle dpm dpm is also equals to beta. Here we get third equation. Okay, now if we write cos beta, how much is cos beta? Cos beta is equals to pm upon pd, right? pm upon pd. And what about cos alpha? Cos alpha is equals to pm upon pn right? Now if we take the ratio of cos beta and cos alpha, we get cos beta or cos alpha is equals to pn upon pd. And since pn is equals to pd, we can write it as pt upon pd, right? And since on changing the position of p, beta and alpha are not getting changed, and that's why we can say that cos beta upon cos alpha is a constant, and we have already taken that it is equals to pt upon pd, right? So we found that pt upon pd is constant. Now you can see this point t is acting like focus, and this line is behaving like directrix, right? You can see that t is that fixed point, and this line, this orange line over here, is the fixed line, such that the ratio of distances of p from this fixed line and this point is constant, right? So here is from where that definition comes. Now at the end, there is a question for you. Can you tell which point and line represent the second focus and directrix? Because we know that in conic section, when we study it on a plane, we find two foci and two directrices, right? So you have to tell where is that second focus and where is that second directrix. Don't forget to like and share our video, and for more such videos, subscribe to our channel Brain Exploders. Thanks for watching.